This section is on what's called z-scores. Z-scores uses a table. Different textbooks use different tables. Some tables or some textbooks have tables where they'll give you the z-score to the left of a score. Some tables will give you the z-scores to the middle. They'll give you the z-score, given a score, it'll just give you the area to the middle. Z-scores give you area. Depending upon which book you use or which table you're using, your z-score might be different than your z-table might be different than the table that I'm going to use. You can go online, type in z-scores or z-score tables, and you will get the table. You could make a copy of the table that I'm using. My table looks as follows. Given any z-score, it'll give you the area to the left. In fact, it's going to have two tables. One that looks like this, where my score is to the right of the mean is in the center. This will be the positive z table. And then you'll have another table where here's the mean, and here is the z-score. Here's the z-score, and it gives you the area to the left. It always gives you the area to the left. Not all z-tables do that. Okay, in the end, will we get the same answer? Of course. Otherwise, this would be meaningless. Two students can't do the same exact problem correctly and get different answers. Now, how do we read the z-table? Well, I'll talk about the positive z-table. In fact, let me draw those two lines in red. Let me do the positive z-table, and reading the negative z-table is exactly the same. There's absolutely no difference, except the numbers will be negative. Okay. So, usually it says z here, and I can't put down all the numbers, but it's going to have start with 0.0, 0.1, 0.2, all the way down to 1.0, 1.1, all the way down to 3.3, 3.4, and 3.5 and up. 3.5 plus, 3.5 and up. On the top line, I'll put all the possible answers. And already I made a typo. 0.00, 0.01, 0.02, 0.03, all the way up to 0.09. 06, 07, 0.08, 0.09. And in the body, you'll see lots and lots of numbers. Those numbers are areas. And they're always less than 1. For example, the number that you see right here corresponds to a z-score of 0.2. 0.2 plus this number. 0.2 plus 0.03. Okay, all these numbers are 1 decimal place numbers. And all the numbers on top are 2 decimal place numbers where the first digit is always 0. That is, what I'm trying to say is this number will be 1.1, and then just say 5. 1.15. That's the z-score right here. Now the z-score corresponds to numbers. And you have every right to say, what number? And it's the number where I put these boxes. The z-score that corresponds to 0.23 is 0.23. It's 5910. 0.5910. 1.14 corresponds to 8729. 0.8729. Now, if somebody gives you a number, so z-scores corresponds to numbers. 0.5910. Z equaling 1.15 corresponds to 0.729. Please don't say 0.23 equals 0.5910, because you know they're not equal. If I give you a number, say I give you 0.9975, and I say find the z-score for 0.9975. Well, you look in the body. The body is here. You look for the area 0.9975. That is, you look for the number 0.9975, or the closest number to it. And I see it. It's where z is, the number to the left is 2.8. The number right above on the top scale is 01. So it's 2.81. 0.9975 corresponds to a z-score of 2.81. We can go back and forth. Z-scores give you numbers, numbers give you z-scores. If you look at all the numbers in the body of the positive z-scores and the negative z-scores, they're all between 0 and 1. In fact, for the negative z-scores, they're between 0.5, and for the positive z-scores, they're from 0.5 up to 1. If z is more than 3.55, they tell you to use 0.9999. You always get 0.9999. Okay, you will always get 0.9999 for all of them. Okay. Now, what does all this mean? First, I should make the comment that everything we're doing with these z-scores is only valid if the problem is stated, or we assume it to be, normally distributed. Uniformly normally distributed. Well, actually normally distributed. If it's normally distributed, that means their data falls on a bell curve. That is, most of the data is in the middle and only a little are on the ends, and it's symmetrical. And since it only goes up to 1, we can talk probability. We can talk probability. Suppose I tell you something, okay, you have a bowling league and their you have a bowling league and their scores, the bowling scores are normally distributed. The bowling scores are normally distributed with a mean of 250 and a standard deviation of 25. Now, this here down here is a number line. In fact, it's 2 number lines. It's really 2 number lines. It's the scores. In this case, the bowling scores. It could have been the heights of giraffes. It can be the weight of leaves on a tree. And it also contains another number line called the z-score. We'll call this X for the scores, the bowling scores, the heights of people. And down here is the z-scores. And every score corresponds to a z-score. And the correlation between the scores and the z-scores is z is equal to the score minus mu over sigma. If you're given mu and sigma, then every z-score corresponds to a particular score, and every particular score corresponds to a z-score. It's just like a number of inches corresponds to a number of centimeters. A different number of inches corresponds to a different number of centimeters. Now we have z-scores and regular scores. So now the question is, now since the total area under the curve is 1, half of the area, 0.5, half of 1 is 0.5, is to the left of mean, and 0.5 is to the right of the mean. Now, the mean in our case is 250. Now, the problem is stated as follows. The bowling scores of a league, of a particular league, are normally distributed with a mean of 250 and a standard deviation of 25. Find the probability that if you pick one player to play a game, their score, which is an X value, their score is less than 275. The probability that their score is less than 275. Well, here is 275. It's a regular number line. 275 is to the right of 250. Here's 275. Less than 275 is this area. And this looks just like our table. Gives you the area to the left. So X, the score. So let's find the z-score so then we can look up the area. X is 275 minus mu, which is 250, divided by sigma, which is 25. This is 25 over 25, which is 1. But we really want to write it with 2 decimal places. So on the top, in the left column, we look up 1.1. On the top column, it is always 0.0. Whether that's 0 down there or not, it's always 0.0 followed by this number. With one exception. If you have 1.0872, since this digit is 5 or more, that's really a 9. So we would look up 1.0 and for the left column and 0.09. Okay, so I'm going to look up 1.0 in the left column, and I'm going to go to the right until I hit the top heading of 0.00. I go to the left column, I go to the positive z-scores, because 1.0 is positive. I go to 1.0, and then I go to the right, not too far, because if I go one number over, I'm right under, look at the top heading, I'm right under 0.00. And that number is 8413. Please don't write that 1 equals 0.8413, because you know it doesn't. Okay, 3 centimeters does not equal to, 1.2 inches. They're not, just because, assume this is true. 3 centimeters is 1.2 inches. 3 doesn't equal 1.2. Okay, Z is 1, and the area is 0.8413. So the probability that your bowling score is less than 275 is 0.8413. which happens to be, if you move the decimal 2 places to the right, 84.13%. Almost 85% of the times, your bowling score will be less than 275. It might be 25, might be 111. That's less than 275. Almost 85% of the times, you will get 275 or below. Now, you may say, but you didn't say you can equal 275. Doesn't matter whether it says equal right here or not. That is, whether it says x is less than 275 or x is less than or equal to 275. The answer is still the same, whether it has the equal line or not. So that's the area. That's their chances, the percentage, the probability that you get less than 275. The table tells you how to find area to the left of any score. Now the score, the value they give you can be a z-score. What's the probability that the z-score is less than 2.54? Well, that one's straightforward, because you already even have the z-score. For the record, z is 0 in the middle. If you think about it, it's x minus mu. But at the middle, the x value is mu. So it's mu minus mu over sigma, which is 0 over sigma, which is 0. Right at their center, at the middle, mu, z is 0. And it's a number line, so 2.54 is to the right of 0. So the probability that you're less than or possibly less than equal to 2.54, well, it's here. Remember, this is the z-score. And once you have a z-score, you can find the area. 2.54. You go to 2.5. You go to 2.5, and then you look under always 0.0 and that number after you round it off, 0.04. So in the left column, you go to 2.5, and in the top column, you go to 0.04, and whatever number you see there, you're done. Write it down. 2.54. 2.54. If I'm reading it correctly, it's 99.45. And that's the answer, 0.9945. Yeah. Right here, you would see 0.9945. And that's the answer. So if you're given the z-score, that's even easier. Now, what if you're not asked to find the area to the left of some score? Now, what you need to remember, I said it at least once, the total area is 1. So if I tell you that this area happens to be 0.73, then you should be able to calculate that area. What you do is you subtract 0.73 from 1. 1 is the whole area. 1 is everything. 1 is everything. And if you take away 0.73, you get what you wanted. You get this area here. You should see it. You should really see it that way. That is, subtraction really works. So this area will be 0.27. This area, the shaded area, is 0.27 or 27%. You take it away from 1. Okay, so having stated that, let's consider the following problem. Suppose that you measure the heights of all 12th grade male students, and you find out that their mean, and it's normally distributed, the heights of all 12th grade students in America are normally distributed with their mean of 67 inches and standard deviation of 5 inches. If you pick a 12th grade student at random, find the probability that their height, which is an x value, is greater than 72 inches. Actually, let's make it 73 inches. Or 74 inches is even better. The probability that their height is greater than or equal to, it doesn't matter, 74 inches. Since it's normally distributed, we draw our famous bell curve. The mean is 67. The height we're concerned about is 74 and above. Even if it didn't say equal to 74, even if it didn't say equal to, I would have said 74 and above. Okay, problem here is our table doesn't tell us to the right of a score. I can find the z-score here. So I can figure out what z is. I can't find the area to the right of a z-score, but I can certainly find the area to the left of a z-score. I'm going to find that area. I'm going to find that area. I'll find the z-score to the left of 674. I like to write z sub 74, so I know it's the z-score for 74. It's the score, 74, minus the mean over the standard deviation. It's 7 over 5. Personally, how I divide by 5 is I double the top and I double the bottom. And then I say, oh, that's 1.4. Just move the decimals in one place. 1.4. 1.40. So I look up 1.4, and then I look at the top, 0, 0. So the z-score for 1.40, well, I go to 1.4 in the left column. Let me actually draw that. I go to 1.4 in the left column, and in the top column I look under 0, 0, and right there will be the number. 1.40 is 9192. 0.9192. Okay, so now I know this is 0.192. I know the area that I don't want. Well, the whole area is 1.000, and that's the whole area. That's everything that I am putting in red right now. It's everything. But then I take away what I don't want. I don't want what's to the left of 74 inches. So I take it away. So from 1, which is the whole area, I take away the area to the left of 74, which I just realized, I just computed to be 0.9192. And that answer is 0808. Okay, so the probability that if you randomly select a 12th grade student and their height is greater than 74 inches is 0.0808. Very little bit more than 8% of the students will be bigger than 74 inches. Okay, what if I go back to the same problem? I tell you the heights of 12th graders are normally distributed with a mean of 67 inches and a standard deviation of 5. I think those are the same numbers. They're not, doesn't matter. And I want to know what is the probability. Now, just like that's the symbol for addition and this is the symbol for multiplication, what I'm writing right now is the symbol for x's in between. This is the symbol for x's in between. X is in between 55 and 65. I want to find, so let's start over. Here's their problem. The heights of all 12th grade students are normally distributed with a mean of 67 inches and a standard deviation of 5 inches. If you randomly pick one 12th grade student, what's the probability that their height is in between 55 and 65 inches? Okay, so need to get that answer. Well, since it's normally distributed bell-shaped curve, I would draw the picture. Maybe not. Maybe if I see what's going on, maybe I'll have a chance to be able to do the problem. Okay. So we know the mean is 67, and we're talking about between 55 and 65. I want to know that area, or probability. Area and probability in these problems are the same. What's the area? What's the probability? Oh, they're the same. Well, the thing is in this problem, I want to find the area. Now remember, every score corresponds to a z-score. So if I only have scores, I really have z-scores. I can use my x minus mu over sigma and convert each of these scores to z-scores. So when I say I have two scores, that's the same as my saying I have two z-scores. If I have two z-scores, I have two scores. Problem, so I have two z-scores and want the area in between them. Problem is our table only gives you the area to the left of a z-score. So here is my strategy. What I'm going to do is the following. Here's 65 and there's 67. If I calculate the area to the left of 65, I meant to write 55 there, not 65. If I calculate the area to the left of 65, which I can do, well then I got a little bit more than I wanted. I didn't want this area that's in blue. But you know what? I can calculate that blue area because that area is to the left of some z-score. Okay, so first let's put this red. So I'm going to find the area of the red and the blue, and then I'm going to take the area of the blue away. The area of the red and the blue, that is the area to the left of 65. I can calculate that. It is 65 minus 67 over 5. It is negative 2 over 5. Double the top, double the bottom, or take your calculator and you find out that it's 0.4, but say 0.40. And if you look up that z-score, now since it's negative, go to the negative table. If you look up 0.40, first go to 0.4 on the left. 0 is 3446. 3446. That's the red and the blue. That definitely includes the area we do want, but then some extra. So I have to take away the extra. I need to take away the blue. The area of the blue, well, that's to the left of the score 55. Let me convert 55 to a z-score, and then it's to the left of that z-score. I can look up that number. Z at 55 is 55, the score, minus the mean, mu, over 5. It's negative 12 over 5 use your calculator, you get negative 2.40, which is still a negative number, so you go to the negative z-scores still. You go to negative 2.4 in the left column, and you just go over 1 to the right. Because right above that number to the right, right above 0.0082, you'll see 0, 0. That second digit is 0. Okay, and that's their blue area. So we take that away. 0082. And what we get is 436. Looks like we get 3364. 34, yeah. You get 0.364. That's just the area that's in red. And that's what we were asked to calculate, the area between 55 and 56. Okay, you have to see it. It's not that hard. You just have to see it. You have to see, well, the rule is I can only calculate areas to the left of a score, whether it's a z-score or a score, like the heights of students, their bowling scores, whatever. The weights of a cake. It's always you can find areas to the left. And if you want to between, well then you have to find areas to the left 2 times. For example, if you want to find the area in between this x value and this x value, well, first you find the z-score here, and that will give you everything to the left. Then you find the z-score of that number, and you find that area, and then you take it away. So you find the z-score here, and then find an area. Write down that area. Find the z-score here, find the area. Subtract the 2. That will give you the area in the middle. Okay. The next thing I want to tell you is just some definition. When they tell you that it's standard, normally distributed, that's just their way of telling you that mu is 0 and sigma is 1. That's just their way of saying mu is 0 and sigma is 1. Okay? Suppose we're talking about the weights of newborn, and they tell you, so here's the problem. The weights of newborns are standard, normally distributed. Find, if you randomly choose a newborn baby, what is the the problem is that the weights of newborns, the average couldn't be 0. First of all, you have to be, for the average to be 0, either all the babies' weights are 0, which is insane, or some are positive, that is, some are more than 0, and some are less than 0. You can't get less than 0. So you take your test, okay, and your teacher says average is 0. 1's a little bit more than average. 1 is just below average. Wait. 0 is average. 1 is a little bit above average. 2 is a little bit more above average. 3 is just below excellent. And 4 is excellent. And I don't want to even think of the words to the left, but you have little below average, more below average, very much below average, disastrous. And I meant to say -2, -3, and -4. So those are the scores that you can get on your next test. I once had a teacher, he would either give you plus, 0, or minus on your homework assignments. These are honestly the 3 grades he would give you. 0 meant average, plus meant above average, minus meant below average. 0 didn't mean you got a 0 on the test. Meant you got, or on the homework. Meant you got a 65, 70. Okay, so suppose you take a test, and also, let's even shade it in a little bit more. That is, you can get any score below 0 and above 0. That is, if you got 211, you're like a rocket scientist. If you got negative 211, you're barely breathing. Your brain is barely functioning. Okay? So the further away from 0 to the right, the better you're doing. The further to the left of 0, the worse you're doing. Okay, so again, you take a test, and the average is normally distributed. So I'm trying to think of something in real life that would really, really be normally distributed. Standard normally distributed. I'm sorry I can't think of one, but I'm hoping you get the point. The mean is 0. That's it. The mean is 0. So you take this test, and again, your grades can be from negative infinity to positive infinity. You take your test, your grades can be between negative infinity and positive infinity. And they look at the people who administered the test, they look at the test, and they go, oh my, the mean is 0, and the standard deviation is 1. Which means it is standard normal distribution. It's a standard distribution. So you have a standard distribution, and we want to know what is the probability that your score is in between 2 and 5. Well, 2 and 3. What's the probability that you get a score between 2 and 3? Well, since it's normally distributed or standard normally distributed, I will draw a bell curve. The big difference is 0's in the middle. And you want to know about getting between 2 and a 3. Well, again, you cannot find the area using your z-table between two scores. You can only find to the left of a score. So I'm going to find this. I want to find this area. So first I'm going to find the area to the left of 3. And then I'm going to take away the area to the left of 2. And what do you know? I'm going to get the area between 2 and 3. So the z-score at 3, I find the z-score at 3, then I can find the area. Well, it's the score minus the mean, which is 0, divided by the standard deviation. It turns out the z-score is the score. I mean, think about it. Z is x minus mu over sigma. If mu is 0 and sigma is 1, you get x over 1, or x. The z-score actually equals the score. So that makes life easier. So now I know immediately the z-score at 2 is 2. So the z-score at 3, which is 3.00, so I look up on the left column on this 3.0, that is a positive table, and then I go over to 0, 0. And what I get is 99.87. This is 0.9987. And when I look up on the 2, which is 2.00, I get 97.72. And I subtract these areas to find in between. I get 0.0215, 987, 0.0215, 0.0215. Every problem, with the exception of this problem here, every problem I've given you, I told you where mu, what the mean, and what the standard deviation was. In this problem, I didn't tell you that. I just told you it was standard normally distributed. That implies that you know mu and sigma. Whenever I hear standard normally distributed, I think two things. Normally distributed, and mu is 0, and sigma is 1. And if you want to even take it up a step, the z-score at any number is that number. The z-score at x was x. Okay, this completes the section on z-scores. I hope it was fun.